In this video, part 2 on energy, we finally tie everything together. We connect why our concepts of work and energy and how they connect to Newton's second law. This leads us to the most powerful and important part of this section of the book, which is called the work-energy theorem. Remember, our purpose was in order to find out when there was speed change and how force was related to that speed change. And we found that that was through this quantity called work. And that work is transferring something, and that something that's transferring is called energy. If a force causes speed to increase, and hence kinetic energy of a body to increase, the force does positive work. This is something that we started talking about at the very beginning. And when we see that the speed of an object, and hence the kinetic energy of a body, decreases, then the force did negative work. That is, it took energy out of the system. So by positive work, we mean it's doing work on the system, putting energy into it. In other words, it's making deposits into the energy bank accounts. And when it does negative work, it's doing withdrawals. It's spending that energy, taking it away from the system. And then sometimes, although you have a force, it does neither a withdrawal nor does it do a deposit. In this case, the force does not change the speed or kinetic energy, and we say that the force does no work. Now, as we've shown in some examples earlier, there are often several forces acting on a body. Some of those forces are making deposits to the energy bank, that is doing positive work. Some are doing negative, they're doing withdrawals, and some are doing no work at all. In order to find out if the body is going to speed up or slow down, we have to consider all the work being done on it. That says we have to find the net work. So you can either think this is the sum of a bunch of works by various forces, or equivalently, it's the work done by the net external force. That is, you sum the forces first together to get one force, the resultant force, and find the work it does. It turns out that while Newton's second law talks about the net external force, and that connects us conceptually to what's going on, the computational side finds it easier if you, instead of adding the forces vectorially, you compute the works individually, because a lot of times maybe you have 10 works. Work by force 1, work by force 2, work by force 3, work by force 4, work by force 5, 6, 7, 8, 9, and 10. 10 forces doing work. And this is to find the net. So if I did the vector, I would have to sum up 10 vectors, either doing them graphically head to tail or by breaking them in components. And then compute the displacement vector and find a dot product. But perhaps in this case, this one does no work, 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 and this one does no work. Well, then I really only need to consider 3 of the forces. So it is better computationally to calculate these many guys, because often a lot of these will actually fall out. And not only that, but we're going to find some tricks to compute some types of works using a function called the potential energy function. And this is going to enable us to calculate these W's faster and easier than it would to be able to add the vectors vectorially. So, although this is the work by the net external force, which is connected to Newton's second law, the way we're going to actually compute that is we're going to calculate the works of the individual dot product for each force separately. And hopefully a bunch of them will be 0. That's why I spent so much time on how to compute work. Let's put all this together. The magic theorem that drives everything, the central concept, is the work-energy theorem, and you should know this one cold. Be able to quote this and write it mathematically for me on demand. The work done by the net external force is equal to the change in the kinetic energy of a body. W net, which could be thought of as being this net external force dotted into the displacement vector, connected back to Newton 2. Newton 2, I told you, knew everything. We're writing Newton 2 in a new way. Is equal, what it does is to change the motion of an object. By doing that, to change the speed of the object. Now, the way to compute this guy, though, like I said, is to actually sum up a bunch of works. Work 1, work 2, ... Now, a lot of times, what you may be doing is that you'll be doing, like on your homework problems, you might be able to calculate K initial and K final, so find delta K. This tells you the net work. Then write down the work for each one of these guys, and then it might be asking you how much work did you do while you pushed this block across this plane, and you need to find this W. But you didn't know the force. Well, that's okay. If you knew, for instance, in a problem, delta K was like 10 joules, you knew that was the case. And you knew that was due to the work of gravity, the work of the normal, the work of friction, and the work that you did, maybe, with some other force. And you find out that maybe gravity did no work and the normal force did no work. Then, and you were asked to find the work that you did. Well, the work you did would be equal to 10 joules minus the work by friction. So even if you didn't know the force you applied on the block in the homework problem, but you knew the friction force and you could compute its work, then you could calculate the work you did without knowing your force. There's several of those kind of tricky problems in the homework. I'll try to do an example in another video, but this gives you an idea that this is an extremely useful thing for doing homework problems. All right. Now, if we're going to have to calculate all of these works, some forces, when you calculate them, it turns out that the amount of work they did depends only on where you start and where you stop, and not upon the path. These forces are called conservative forces. So if you have a conservative force where you want to calculate the work done from going from here to here, A to B, and you get the same answer whether you go like this or if you go like that, or if you go like this, then it's possible for us to define a function that will tell you how much energy in essence you have in the bank here, figure out how much energy you have in the bank there, and subtract the two to determine this work value. This is known as potential energy. And it says the work by a force that's independent of the path is minus the change in the potential energy for that force. Now, first of all, you have to know you have one of these forces that doesn't depend on the path. Some forces do. So if you don't know that it has this property, you can't assume it. But certain ones do have this property, useful ones. Gravity has this property. Springs have this property. So what we're going to do, we're going to give you U formulas. A way to calculate the U here, a way to calculate the U there. You subtract the two values and find delta U. You multiply by -1, and that's the same thing as calculating the work done by that force. The advantage is it's going to be a lot easier with no dot products, and you're not going to have to deal with any vectors if you know this formula U called the potential energy function. Now, one of the things to note about it is only change has meaning. Okay, because it's related to work, and it has no meaning to talk about work without displacement. So only change has meaning. You can't really talk about potential energy at a point in space. So people say, what's the potential energy of the block at height y, 2 meters above the ground? That's really not true. That's a bad statement. What they really mean is if I call the potential energy 0 at the ground and I raise it to 2 meters, what's the change? Only change has meaning. We'll come back and deal with this a lot more later in the course, because potential electropotential energy divided by charge is something called voltage, and it means that only voltage change has meaning. And yet people often talk about the voltage on a power line, which isn't really right. So I want to put this in your notes. I realize that at this point it probably is somewhat vague and difficult for you to get a handle from. That's okay. It should be. But after we do a bunch of problems and get some practice, you should get a better feel for it. The main thing to note is the reason we have potential energy is a way to calculate the work done by these forces called conservative forces, whose work done is independent of the path that they take. It only depends on the starting point and the stopping point. So if you take this path, I'd like you to write the mathematical expression of that path. I'd say, man, that's hard. I have no way of working that. What if I just went and did this path? The answer would be exactly the same. So a person, someone besides you, can compute it for this path and write you that answer down, and then you can use it for any complicated path between those two places. As an example of how this is really useful, to kind of finish this up, remember my problem with the bowl? And I had the ice cube up here, and I wanted to find out how fast the ice cube was going here. It turns out, because gravity is independent of the path, instead of following that path, I could follow this path. I could drop the cube straight down and then slide the cube across. So it'd have two parts. But the work by gravity on that path there is 0, because the force is like this and the displacement's like that, perpendicular. Here, since this is a radius of a bowl, this distance is r, and the gravity, the weight, is mg, so that's equal to the work. So we'd be able to say, hey, mgr is equal to delta k. mgr is equal to 1/2 mv final squared minus 1/2 mv initial squared, but it started at 0. So gr times 2 is equal to vs squared, though the final speed is the square root of 2gr. Did I work the complicated path of going along this curve? No. I took advantage of the fact it's conservative and computed the work for a simple path where it went straight down and the force and the displacement were aligned. Would I do this normally? No. What I would have done is I said, hey, delta u is equal to u final, which is 0, minus u initial, which was mg, and the height, which is r. Work is minus delta u, mgr. Potential energies are just a way to calculate works quickly. We'll pick this up in another video.